Hey folks, we're going to talk about PN44 Part B here, where we're going to give you some more limit strategies. So as we said up here, right here, it says strategies that we have had so far really is to use the graph. So to look at the graph and go from the left bound and the right bound and see where that graph takes you along that path. There are a few other strategies that we can use, and those are what we're going to be talking about today, and specifically strategies that don't always use the graph. So what if you don't have a graphing calculator on you? Well, the first strategy, which is a strategy you always use, is direct substitution. And what that means is really you're taking the value for the limit as x approaches 4 and literally putting 4 into the value for x. So substitute that value in, hence the word direct substitution, and see what you get for the y value. And in this case, you would get 9/5. So the limit as x approaches 4 is going to be 9/5. And so you can do that also with this example right here, where you take that -2 that x is approaching and put it right in for your x. So -2 quantity squared, and of course we know that -2 squared is 4, that quantity squared is 4, excuse me, I'm going to say that again, -2 quantity squared is 4, times -5 is going to give you that -20. So that would be your limit as x approaches -2. Now that up here it says when will this method work? It's really when, and this is really important to note, when the function is continuous at the point or a point. So what's happening is that we don't have that point of discontinuity or any of the other discontinuities that we've talked about at the beginning of the year. So direct substitution works when the point is defined at that x value. So at 4 we know the point is going to be 4 9/5, and this point is really -2, -20. So if you have a continuous point there, then you'll have a limit, and that limit can be used, you can use it, this direct substitution. Now I do want to say this is what you always try. So if you don't have the graph, and now if the graph is given to you, just use what we did earlier in the part A. But if there isn't a graph, always direct substitute the limit in to see what you're going to get. Now here's the thing though, that doesn't work all the time, and as we'll see here, when you put in, let's say, the value, in this case limits to infinity, you can't obviously you can't do that. You can't put infinity in. But we did deal with some of this again at the beginning of the year, and we had a strategy, and that strategy was to use algebra. Now, of course, I showed you how to do it in the graphing calculator and all that at the beginning of the year, and then I showed you how to do it algebraically. And what we did was we divided each term. Oh my goodness gracious, sorry you guys, give me just a minute, let me try that. I can do better, Okay, and you know what I'm going to do? I'm going to stretch, oops, I can't remember how to stretch it out now, hold on. There we go. Divide each, oh my goodness, and each term in the numerator and denominator by the largest, and I could say largest degree or largest power in denominator. And you may have a better way of saying this, denominator. But let me just show you what I'm talking about, and hopefully it'll ring a bell from what we did at the beginning of the year. So what we do is we look at this limit, and we're going to infinity, positive infinity or infinity, And I notice in the denominator I have x cubed. That's my, or the degree of 3 is my largest. I'm going to then divide this by x cubed, this by x cubed, and this by x cubed. And I'm going to simplify that. So I end up with 5, because it was 5x cubed over x cubed, so we end up with 5 in the numerator. And in the denominator, we have 8 over x plus 7. And then what we would do from there is we would take the limit as x approached infinity, and we would substitute, direct substitute, infinity into where the x values are left. And so I have 5 in the numerator, and in the denominator I have 8 over infinity plus 7. And we know 8 over infinity, anytime you divide a number by a bigger and bigger and bigger and bigger number, it approaches 0. So we know that 8 over infinity, or 8 divided by infinity, is 0. So what we have then here is we have 5 plus 0 plus 7, so 5 over 0 plus 7, which is just a limit of 5/7. So again, we did this at the beginning of the year, but I have a feeling many of you may need the review. So let's do that same process here to show how it works. And so I am going to first, and now notice we are, in this case, substituting negative infinity in once we do that trick of dividing each term by the highest power in the denominator. So the denominator here, I see the highest power is x squared. Oop, I have to switch this over. So I'm going to divide this by x squared, this by x squared, and up here by x squared. And so now I can change it. So we have the limit as x approaches negative infinity of really 4 over x divided by 2 plus 1 over x squared. And I know that looks nasty, but now, again, we're going to put infinity everywhere there's an x, or negative infinity, I should say. So I have 4 divided by negative infinity over 2 plus 1 over infinity squared. Now, again, 4 divided by any type of infinity is going to equal 0. And you know what? I can even do one better because I have colors here. Give me just a minute. So we know this approximates 0 because 4 divided by any very, very big or very, very small number is going to make it go to 0. And we also know that this equals 0 because 1 over infinity squared, or negative infinity squared, just means it's going to go to 0 quicker. And so we end up with, ooh, I need to switch colors here, hold on, oop, I don't think I was in that color before, but 0 over 2 plus 0. And that means that we have 0 over 2, which is the number 0. So that is our limit as x approaches negative infinity for that function. Now again, you can graph it. You can graph it and you'll see the same pattern that we're seeing, but that limit is going to be 0. And this is the algebraic way of finding a limit when you're going to infinity, or in the bottom case, negative infinity. So we have two strategies right now. We have the direct substitution, where you can just substitute the values in. Oh, that's cool. Okay, they're going to wonder why I'm saying cool. You guys will have to ask me about my sand display. Sorry, I'm distracted. And then the other method, of course, is what we were just doing with that algebra, dividing out by your highest powers from the denominator. And you know what, this one right here, this last example, we're going to do it super fast. I'm going to divide this by x, and this by x, because that's my highest power in the denominator. So I'm going to take the limit as x approaches infinity of, and we end up with negative 2x up there. In the denominator, we have 5 minus 9 over x. Again, we know what's going to happen here. This is going to equal 0. This, though, this right here, when we put infinity in there, in that top, I don't know if you can't see me pointing, so that's going to, when you put infinity in here, you end up with 5 minus 0 down there, so 5. Negative 2 times infinity is a very, very large number called infinity divided by 5. So you, technically, I mean, you could say you are ending up at negative infinity, but the reality is that there is no limit. So we already talked about where if you go to infinity or negative infinity, that means you do not have a limit. You're limitless. So you do need to say no limit there. Okay. So strategies 1 and 2 can be done with no calculator. We love that, and that's just something you always want to be able to do. But then sometimes, well, that doesn't always work either. For instance, example number 1, we're not going to infinity or infinity, negative infinity here for this limit. We're approaching 9. If I put 9 into this expression, it'll end up giving you 0 in the denominator. Actually, let's do that. 9 minus 9 on the top will give you 0. Over in the denominator, you'll have square root of 9, which is 3 minus 3, it gives you 0. So that's a very important pattern, that 0 over 0 that I'm going to talk about in a minute. Because if you get that pattern, you're going to want to graph it, or you can simplify it using your algebra. This one's not so quick to simplify, but you can graph it and actually look at what happens as x approaches 9. So I will tell you that most of the time your limit does exist. It just doesn't seem like it at first. Does exist. So for instance, what we're going to do is we're going to go, and I'm going to try here to go to Desmos because I prepped it here, Desmos, and show you what this graph looks like of x minus 9 quantity divided by that denominator of square root of x quantity minus 3. Now, there we go. So this is what your graph is going to look like, and I'm going to tell you, if you don't have Desmos on your iPad, you really want to because it's awesome. But we want to see what happens to as we go on towards 9 left bound, let's say. Okay, so I'm going to click on this, and oops, I'm way over there. So I'm looking at those x values, and actually I'm going to zoom in here a little bit. And on Desmos, you can just go along it, and here I'm going, oop, I passed 9. Here's 8, getting close to 9. And 9 is technically undefined. How would we know that? Because when we put 9 in direct substitution, it's undefined. But notice that right to the left of it, when you're at 8.9, you're at 5.992. And if you go the other way, if I'm going to the right bound, I'm going towards 9, I'm 9.2, 9.1, and when I get close to 9.1, oops, I'm at 6.017. So if you look at that, it's very clear that whether you're going from the left bound or the right bound, you do have a missing point there that's undefined, but that point is going to make sense at 6 if it wasn't undefined. So the limit as, whoops, I'm kind of going. So as again you get closer and closer to 9, it's getting closer and closer to 6 for the y value, and then it's undefined, and then the same thing from the right bound. So algebraically, this isn't going to work out for you very well, so you're going to want to look at your graphs. So in this case, when you look at your graph, you must check from the left and the right, and at that very moment, or look at your table, and what you can say is that the limit of this is going to be 6, without a doubt. Now, I'm going to come over here, example number, or there's no number, this example right here where you're going the limit as x approaches 0, 1 over x. Again, this is not 1 to infinity or negative infinity, so you can't do the trick of the second strategy. It's not going to work by substitution because you're going to end up with this pattern, which I'm going to say is another different type of pattern that I'm going to show you what kind of tends to happen with that. So I'm going to go to Desmos again. I'm going to try here. And I'm going to turn this one off and this one on. And so what we're looking at, here's the inverse variation or the rectangular hyperbola. And as our x gets closer and closer to 0, I don't know if it's not going to let me click on it for whatever reason. Hold on, let me do this. There we go. As we get closer and closer and closer and closer to 0, left bound, oops, you can't see it anymore. Notice it's going to negative infinity. I'm just going right on down. And of course, if we go from the right bound, same thing's happening, but we're going to positive infinity. So we know if you have one limit that's negative infinity, one limit that's positive infinity, that just means, first of all, there's no limit, period, and it's not even the same limit. So that's very, very clear to us what's happening there. Notice the next one in your note guide, it says what happens to when you take a limit as x approaches infinity. Well, as you go on your graph closer and closer to x as it goes to infinity, look at those y-coordinates. Look what's happening. It's getting closer and closer and closer and closer and closer to 0. So it's pretty quickly done with the graphing calculators. I have to figure out where my notability is here. There we go. So we answered both of these questions right here. It says find the limit as x approaches 0, 1 over x, and that's going to again give you that 1 over 0, and we know that that limit does not exist, or no limit. This one down here, when we did this one, we would have ended up with 1 over infinity. That doesn't make any sense, obviously. Actually, 1 over infinity, if you substitute it in, you can really kind of say, hey, you know what, that's 0, and that is exactly what happened, right? So I just want to say, if you end up with 1 over 0, oops, the pattern right here, you tend not to have a limit. So limit does not exist when you have this pattern. Limit does not exist. So if you have 0 over 0, a lot of times the limit exists. 1 over 0, limit doesn't exist. So those are just a couple patterns that I wanted to make sure that you were aware of. Now, the last two examples, I'm going to have you do those two as an example, and you're going to show those to me in class. And I would highly stress again, you graph it. Notice you can put sine of x, sine of 0 in, substitute in first to see what happens. So, and you know what sine of 0 is, over 0, and see what kind of pattern you have. And then from there, look at your table and your graph and decide what kind of limit you have. Same thing here, you first should probably substitute in. You'll see that you end up with a certain type of pattern, and then decide what kind of limit you have. And again, use Desmos. It's really, really easy to do it with Desmos. So those are the three big key strategies that I wanted to share with you. It gets a little bit more complicated in the sense of the strategies, but not too difficult otherwise. So again, the direct substitution is the first thing you want to do, always to check to see your pattern. From there, if you have an infinity one, obviously this strategy 2 is really something we've done in the past, which is powerful. And then last but not least, look at your 0 over 0 or 1 over 0 and note that the limit does exist if you have a 0 over 0 pattern, and the limit does not exist if you have some sort of number. I shouldn't say just the number 1, some sort of number, any number. It could be 20 over 0, but if you have a number over 0, the limit will not exist. So we will take questions in class, but I hope you enjoy this video. Take care.